Okay, testing, testing. How are you hearing me, Cameron?
Yeah, you sound good.
Okay.
You sound good.
At 10-4, it's all clear.
Fantastic. Okay.
MIRI is one of the 4 instruments on board the James Webb Space Telescope. It's the one instrument on board the telescope that will be observing at mid-infrared wavelengths. The other instruments focus on the near-infrared part of the spectrum.
NIRSpec, NIRCam and the FGS, they work at wavelengths from about 1 to
4 or 5 microns. Now, MIRI is unique on the James Webb because it operates at even longer wavelengths than that. So we start at 5 microns and we keep going out to 25, 30 microns.
MIRI is actually quite a complex instrument. It has several different observing modes on board in the instrument. So we have a camera that just takes images in lots of different filters across the mid-infrared wavelength range. We also have spectroscopic modes, so we have low resolution spectroscopy, and we also have a medium resolution integral field spectrograph.
When you look inside our own galaxy, you can see dusty regions, and there's things going on inside those clouds, inside the dust, that you can't see because dust is essentially opaque. If you move out to longer wavelengths, out into the infrared, the opacity, the amount of light that is absorbed by that dust drops. And so we can see not just the surface, but into the heart of dusty region. So that means we can see to the center of our own galaxy more easily. We can see inside dusty regions where stars are being formed and see them, see what's really going on when a star is formed in space.
We're really going to be able to address a huge range of science questions. MIRI is going to be able to probe even further back into the history of the universe. It's going to be able to really study the atmospheres of planets around other stars and really be able to kind of search for the signatures of molecules in those atmospheres. Those are just a few of the highest kind of profile science goals that we hope to achieve with MIRI.
Well, hello, everybody. This is Scott Roberts from Explore Scientific and the Explore Alliance. I think that was kind of a cool fireball experience there. Everybody loves a good fireball. So today, on today's show, we have Jerry Hubble joining us. Ross Ferguson is with us as well, and Cameron Gillis. And we're going to cover, Jerry and Ross are going to cover, common imaging errors, and maybe how to correct those. Cameron's going to cover drift alignment method, which a lot of people have asked questions about. We created a document so you can kind of follow along, but we'll see how Cameron wants to present this. In the meantime, nice to see all of our people here logged on into to the show and also into the audience. And so I'll let you guys get started.
Is this I imagine is a little different audience than what I'm used to, people showing up at the OpenGo2 broadcast we do on Tuesdays, Scott, is that correct?
A lot of the same people.
A lot of same people?
A lot of the same people, but every time they watch a different program, it's a little different, so.
Well, and we're getting people that call every day. And so I have the opportunity to say, hey, you need to go check out our Focus on Astrophotography show. So we are getting some different viewers, Jerry, and we are certainly excited about that. I'm so excited too, because I was speaking with a friend the other day and he had watched some of our videos and he just said, you must feel so cool getting to come on and talk after videos like that, like the videos that our Captain Roberts brings on every episode and shows to us. It's fascinating and it really makes it feel special. And then, I've got National Geographic and Discovery and Explore Scientific logos behind me. And, I grew up with the National Geographic magazine, just stacks and stacks of them. So it is just a tremendous honor that I'm so grateful for every Friday. And passengers, I'm really glad you guys woke up, because this is going to be an awesome show. I think it's going to be so fun. And Jerry and I, we're gonna do some good work for you today. And Cameron, of course, drift alignment. If you can't see the North Star, or if you just want the perfect alignment, that's how to do it. And I have no idea how to do it. So as we've told you, we're all just learning curve together. And so we're really excited to get up to the top of it right now. And we've got the guy here that knows how to get us there. We have, you know, the atom crushing, the code writing, the plane flying, moon loving, project man, Mr. Jerry Hubble, and he's going to tell us a lot today. But first, Jerry, if you don't mind, I would really like to show some of the work that the MSRO, the Mark Slade Research Observatory, that you are the vice president of, among many, many things you do, whether it's nuclear physics and all of that, or just writing code for us. But here on the mothership, Jerry is known as the source code creator, and I'm going to share a little research of share my screen of some science. And so here we go. Oh, still on that. Let me try one more time, guys. Here we go. Okay, so this is one of the observatories there, and
Yep, that's station 1.
that's station 1. And what telescope's inside that, Jerry?
That's the venerable Explorer Scientific 165 FPL 53 flagship telescope we have. It's an awesome telescope. It's mounted on the Losmandy G11 system. We have PMC8, and it works great. We've had it there for it'll be 3 years, or almost. It'll be 4 years on January 1st, I think, that we installed it.
Well, I'm trying to get this to work here. It's always, you know, just like astrophotography, is never going to go exactly the way you hope it to. But I'll do one more screen share, Jerry, and then I think it's going to be golden. Here we go. All right, this you all are going to love. This is my favorite. We've got the man, the myth, the legend.
Oh yeah, it's in a F4U Curtis, right?
Corsair, yep.
Corsair, that's right.
Yep.
I remember watching the Black Sheep Squadron when I was
Yep.
a kid.
Exactly.
That was awesome.
I would
That was
love,
one of my favorite.
I would love to fly in that plane. You know, I think
Yeah.
it's really, I don't think there's room for 2 people in it though. I think there's just one.
No, it's just one. I actually I didn't fly it. That would have been awesome, but I wasn't. I'm not qualified, of course. But I got to sit in it for an hour and talk to the pilot about it and go over all the controls and walk around it as if I was going to fly it. So that was pretty awesome. This was at an air show in Culpeper, Virginia, at the airport there. And it's just great to be able to talk to pilots and get into that whole in the aviation community, like it is with the astronomy community.
It's so cool. I mean, those Corsairs, when you see them right there, they're huge. I mean, the engine, the engine, the wings of that thing is a big. It's a real. It's a tough. It's built like your Exos 2.
It's like a tank. Yeah, exactly. It's like a tank.
It's like a tank. Yeah.
That ball wing and stuff. I mean, just
Flying tank.
really,
Yeah.
really cool. So that plane, the P-38 Lightning, and of course Britain's Spitfire, and our Mustang. Those were just incredible, all incredible aircraft. So.
Oh, yeah. Very awesome.
Mm-hmm.
Yep.
Well, I told the passengers Jerry does love the moon, and so when there's a full moon, that he can't get the deep sky objects, and so that's what he's shooting. Here's one of his photos here from the Slade Research Observatory.
That's one of the few full moon images that I've done in the past. I'd like to do. I'm kind of contrary. I use a astro camera. We don't change the camera out on the main instrument, so I just make do with what I have, basically, which is the astro camera, and the system does excellent high resolution work, even with the 850 millimeter focal length, which is a little short to do typically if you want to really zoom in to do very high resolution. But again, you're able to see objects down to 2 to 3 kilometers pretty easily with these images, with the full disk image of the moon.
It's located in Wilderness, Virginia. Is that correct, Jerry?
That's right. Wilderness, Virginia.
There's got to be a dark sky out there.
It's pretty dark. We do have, we got Fredericksburg to the west of us, and then we have Charlottesville and Washington D.C. to the north. Oh, that's one of my favorite.
I
like doing black and white.
Scientists can take pretty photos too.
Yeah, I like doing black and white. I always liked black and white astrophotography, even though the colors are pretty. I don't know what it is. I'm just a black and white kind of guy. I did film back in the day, black and white, so that's why I like it.
Yeah. Well, and this was only 30 minutes. Again, all these pictures you'll see is from the Mark Slade Research Observatory, and it's open to the public. Now, this is just kind of honoring, this is our mount at Explore Scientific. Well, it's the Lowes-Mendy mount with our PMC-8, and it's available on our website. Jerry got that hot product of 2018 Sky and Telescope, and that's a tremendous honor. So you all should know it's a fantastic piece of equipment. And oh yeah, the smaller one too. So whatever weight telescope you have, we've got the mount for you, and we will get you tracking under that 2 arc seconds. Tell me about this, Jerry, because this picture just said told me I got to get out there. I want to be wherever that telescope is.
This is a photograph. You got this off of the MSRs or off the
Yes, sir.
Where'd you find that?
Of their Facebook page.
Oh, okay. So this is a post that Myron posted. He's into classical older telescope systems that he refurbishes, and this is one of them. I think I'm not exactly sure which scope it is, but you can see it's a long focal length refractor on a pier.
It looks like a
Very
unicorn or something.
Yes, I don't recall seeing this image particular. I've seen the scope before, but I don't remember this image.
Yeah.
Okay. Well, there's this I liked. This was from your all sky.
Yeah. Right. So we've got an all sky camera at the observatory, and this is showing, I believe what Myron's showing here is the difference in when there was a lot of fire going on or something. I don't remember last year.
You're exactly right.
September.
You're exactly right. Yeah, these are the fires in California, and I just thought it was interesting to show our audience how things everywhere can affect your pictures.
Yep.
So
that's a great example.
We're about I should have wrote down the name.
It's Hubble's variable nebula.
I need that one. I need to take a picture of that.
Oh, I love this one.
Change.
And it does, and it's quite bright right now. Actually, I took a picture of this, Jerry, if you recall, earlier this year, with my smartphone, and I was amazed how bright it was at this time of year or this season.
Right,
it's a beauty.
That's got to be my next target or something.
That's something that you want to continue to observe and take pictures of, because it will change. The light, the pattern changes, and the nebulosity changes. It's kind of cool to watch over the seasons, over the years, how it changes.
And there's some texture, in it too, right, Jerry? I mean, you can see some of the structure in it as well, which is really nice.
This, this is a Facebook image. I don't have the high resolution.
Yeah, here's some other. So Myron took these photographs. This is he likes these little faint fuzzies, like you guys do. So he's into that.
Well, I got some of those, and then you're gonna have to explain this to me, Jerry.
Okay, so this is a nova that's recent, back in March. It looks like, and you can see the emission on the H alpha and H beta lines there, is what it's showing there. We have a spectroscopic grading in our two of our stations, the main station and station 2 or 3. I can't remember which one it's mounted in, but this is work that Myron did again, that shows these emissions from the nova. Okay. When it was blowing off hydrogen. It's blowing off hydrogen. Would this
be with a hydrogen filter?
Oh yeah, it'd be very bright. That's what those peaks show you. So they would be very bright. It's blowing off hydrogen, and that's what the nova was ejecting.
But yeah, the stuff here at the bottom, that's very cool. We've got a few other pictures. I I noticed as I was going through the pictures at Mark Slade Research Observatory that there have been a ton of supernovas this year, or I mean, at least it
Well,
seems.
Myron tries to take images of the different supernovae that get announced and do spectra whenever we can. That's right.
Yeah, so we do have some spectra. Just this is going to be supernova.
Now these aren't pretty picture type pictures. These are science images, so you can to document, what's going on basically.
There we go. We saw that one. Okay, I thought I had a few more, but I'm not seeing them on there, so we're okay. We had some more spectroscopy images, but what I can tell you is you can get on and you can control that telescope that's taking those pictures.
Yep.
And Jerry will be the one to show you how to do it, and he helped me. I got to see it. It was really awesome. And if you want to do some science, if you want to feel like your pictures need some meaning other than just looking pretty, your work at the MSRO is going to the International Astronomical Union, the Minor Planet Center, the NASA MIT Transiting Exoplanet Survey Satellite. So, I mean, you can take pictures that is going to find some exoplanets. Exoplanet Follow-Up Observing Program, the AAVSO, the Variable Stars.
The stars, there's a ton of data. We've taken a ton of images over the last 5 years that is ripe. They're ripe for doing some analysis to pull out all the variable stars and do measurements with those. We haven't done that work. We've enlisted, we've got students that have done work at our observatory, and we've got these different projects like that we can do for students. Students can get involved. Anybody can get involved.
Yeah, well, Jerry, I'm gonna let you take over now, and if you wanted to share and talk to us a little bit, and then we will move to the stellar imaging aids. But
one of the things we can talk about is I don't know if you wanted to talk about the equipment a little bit. Is that right?
Well, I certainly do, because I think a lot of our passengers might just assume that it's a telescope you can buy, and you probably can't do science with it. Like I assume passengers think a 4-inch telescope is incapable of doing science, maybe.
No, it's very capable. In fact, if people don't know, the TESS mission, the Transiting Exoplanet Survey Satellite, is made up of four separate telescopes that are only 4 inches. Believe it or not.
Really?
They're kind of like a finder scope. You see the observatory's desktop now?
Yeah.
You do.
All right, so I'm going to be looking sideways, so you'll see me looking at this other screen. But in terms of the TESS mission, it's made with they're 4-inch telescopes, and the image scale is kind of weird for us. Since the surveys and the telescopes are very wide field, they're like 20 some degrees.
Jeez.
Okay, 25 degrees field of view or something like that. So the image scale is very poor for typical imaging. It's 21 arc seconds per pixel.
Wow. So it's 105 millimeter aperture lens.
Right.
Looks like it looks like a photographic lens, like you would get for like a Canon or something.
Like a Canon, right?
Right.
Yeah.
The field of view on those things are 24 degrees by 24 degrees.
Yeah, I thought that was about what it was. Yeah. So the problem is when you're looking for exoplanets and you got pixels that are that big, you could have several stars that are in that one pixel. Okay, and then in a group of pixels, when you're diffraction limited, you'll have a profile. The point spread function, of course, and so you'll have the light of that group of stars spread over in that profile. There'll be like maybe there could be 20 stars in that one blob of light, right? So when you have that many stars in one blob, you don't know which one's the exoplanet. You have no idea you might have a signal that looks like an exoplanet signal that's actually a variable star, or an eclipsing binary is typically what you find. So you need to screen that stuff out. You need to weed it out to see if there's really an exoplanet there or not. So that's the problem with the TESS is kind of like a finder scope in that regard.
Oh, okay.
So you could think of it like that. And then it relies on the ground observers to really figure out where the real exoplanets are based on the TESS mission. So that's why it's very important for citizen scientists to help in that regard, because there's, thousands of stars that might have a signal, or they detected thousands of objects of interest is what they call them, that need to be screened and surveyed from the ground to say, okay, where's the real exoplanet? Is there a real exoplanet here, or is it an eclipsing binary, or is it something else that's going on? That type of thing. So, and that
Hey, Jerry,
way,
will you explain what PSF means, point spread function?
the point spread function is basically a graph of the light looks like when you zoom in on a star. In fact, let me do that here. Let me see if I can bring that up. So I'm going to use that program that we use to control our observatory called Maxim DL. It's got some image processing tools in it. So I'm going to see if I can find a I'll pull up an image that I took the other night when we looked at an asteroid. Persephone was the name of the asteroid. So you see how the light's kind of spread out across several pixels?
Yes, sir.
Like right there.
Mhm.
See that? Okay, so let me bring up the graph window here, and I'll draw a profile. This will give you, let me see here, I'll do a horizontal box. So I'm just gonna, there's a profile. Okay, so that's a point spread function. All right, it's a Gaussian shape.
Okay. Okay.
All right, so the point spread function basically is the function of the light. There's one that's smaller. It's not, it forms a bell-shaped curve, basically. That's the profile, okay? Actually,
And that's the amount of light.
That's basically the light. Let me go to a bigger blob and we can see what it looks. It might be a little smoother to give you a better idea. So there's something that's a little smoother. It's got more pixels. Okay. So that's what the point spread function looks like. Okay, now it's not really two-dimensional. The star is three-dimensional, or I'm sorry, it's not two-dimensional because you got an X and a Y axis on the star. So if you look at, so let me plot that.
And what is that telling us? So
that's just basically a plot of pixel position on the x-axis, which is the horizontal axis, to the brightness of the pixel, the sum of the pixels in a y-axis. So right now, so let me draw, instead of a box, I'll draw a line through the star. Okay, so right there you go. Now I'm gonna do it a little different here. I'm gonna draw a line, but I'm gonna use the box function because I can limit it.
And so what do our passengers want that graph to look like? Is there a certain thing we're looking for?
Well, this is what it's going to look like. This is the way a diffraction. This is a diffraction image of a point source, is what it is. So remember, when you're diffracting, because you've got a limited aperture, it's 4 inches or 8 inches, whatever the aperture is. There's, the edge of the glass is diffracted into the image, right? So that's what that does. So it's not a point source. It's not going to render it as a single pixel, unless you're unless you have a huge mirror like the Hubble Space Telescope will render, I imagine, stars as single pixels, depending on how bright they are. But the fact that you have a finite size lens causes it to diffract and causes this profile. There's nothing. That's just physics. That's just the way it works.
So
And
Jerry, is it
Cameron may
fair
have
to-
something to say. Yeah.
yeah, I was just going to say, optically, when you visually look at this, you're actually going to see airy disks, correct? This is
Yeah. So right.
this is
So
actually the rings of the airy disks are the construction and destruction of the light because of the nature of physics. But when you look at it with a instrument like this, it spreads that out, right?
well, this is kind of like the way the airy disk is rendered on image when you're doing a time exposure, because the noise and you're accumulating light, it's the
yes,
profile is smooth.
it's a
Where
smooths
your
it out
eyeball,
exactly.
right? So you could render this, if you bring this out of focus, you can see the airy disks, the rings on the airy disk, right? But
Yes.
when you focus it and you bring them all together, then it smooths it out and makes it this profile basically. So you're correct. The airy disk is a manifestation of the diffraction of the lens.
Yes. And for those mathematical folks out there, it's a bezel function.
Yeah.
Yeah.
So let me show you so this is the 2D or 1D render of that star. So let me show you what an area plot looks like. That thing's
Okay.
so you can tell this star is overexposed. You can tell that because the top is flat.
Flat.
Okay.
Okay. Okay.
And then the other thing, this is looking at it from the side, but let me move it around. So now this is what it looks like.
That's
All
our
right. So let me go to another star and we can get one not quite so bright. Maybe this one's not quite as okay, there you go. So that's what it looks like. That's the brightness plotted over the X and Y plane of the image. That's the
So
profile.
the colors are representing you know,
the brightness.
dominant. Okay.
Yeah, the brightness pretty much.
Okay.
Let's see. Let's look at this star here. That one's overexposed too. You can see again that it's flat on top. And you can move this around to look at the profile, and you can see there's a little dimmer star there. This one right here.
When you get to the red contour, which is clipped to your point, that's basically when your pixel well depth is saturated, right?
That's right. That's when you're saturated, right?
Yeah, you can't get any more photons.
And you don't really want to. You've talked about that in the past in terms of setting your exposure for objects and stuff. You don't ever really want to overexpose, especially an extended object. And I'm sure Ross and Cameron can talk to those points very well. So this is what the background looks like. You can see the noise in the background. Now this is not a calibrated image, so
It's so interesting. It really is. Like,
yeah, and that's why you won't get the signal to noise really good, because then all those little bumps and ripples get diminished.
right, exactly. So the Maxim DL provides a lot of tools to do analysis on images, not just to and then do color processing also and things like that. It's a pretty nice program. It costs some money. I mean, it's for me, running the observatory, having a good quality program, although there's a lot of free ones out there that are really good to run your observatory, having a professional level program really helps to keep an integrated system and makes it easy to run. And the biggest goal when you're running a permanent observatory is you want to there's two things. If it's a teaching observatory like what we have at the MSRO, then it's a hands-on learning environment, and you want to be able to bring all the features and functions you can to show people how to operate the observatory. The other side of it is that you want to have a good system to where it runs, it's reliable, it can start up very quickly, and you can just use it, right? You want and Scott and I talk about this all the time, we want our equipment to disappear. We don't want to have to mess with it. And that's why we use the telescope drive master, because we don't have to worry about auto guiding. That's a whole nother system that we can do without. And that's what Elon Musk always says, and I agree, is that the best part is no part. The best function is no function. Anything to simplify your setup, is going to add value later on. Sometimes it's hard to to learn that lesson. It depends on what your goals are with the hobby too. You know, if you like messing with equipment, then go for it. You know, learn all you can. I do. That's one of the major parts of the hobby for me. But when you want to concentrate on your imaging, that's all you want to care about is the image, right? You don't want to mess with, and Cameron can talk to this, I'm sure Ross too, even more than I can in some respects.
Yeah, I like a bit of both. I mean, but to your point, you know, to keep it fun and have keep up a good solid pace of sky survey, you wanna roll in the kind of the tinkering with and spread that out because everyone only has so much time in the day, right?
Right.
So
tinkering's a big part of the hobby.
It is fun. It's really fun, but you can really spend a lot of time, and then I was like, oh shoot, I need to do some other stuff.
Right,
yeah.
right.
Hey, Jerry, I got a question about the telescope drive master. I'm not sure our passengers know what that is either. And does it works on numerous?
Yeah, I can demonstrate it. I can demonstrate it for you and give you an idea of how it works.
Yeah. And is it just a piece of equipment?
It's a high resolution incremental encoder that goes on the right ascension axis, and it corrects your tracking rate, basically makes it near perfect. Now there are some.
It basically eliminates PhD, right?
Yeah, it takes the place. You don't have to, if you've got with a permanent observatory, you're going to have a near perfect polar alignment. So you don't have to worry about declination drift. This only corrects the right ascension axis. Your declination is not going to drift, of course, because you're not moving the motor. Yeah, your polar line, you're not going to drift in declination. And all you have to do
I have
now
to have
is
sorry, Jerry. Sorry. Do I have to have a certain mount for this telescope drive master?
it can be used on several different mounts. We do offer it on the Exos 2 PMC8, on the G11. It has to be worth your. It's almost like you could mount it on the IXOS 100, but it's a lot more expensive than the IXOS 100. So
exactly,
it depends on your budget, but on a G11 class telescope or mount system, it works great even on the Exos 2 mount, even though it's more expensive than an Exos 2. It's about twice as much as what you're going to pay for an Exos 2 mount PMC8. It still is useful. I mean, it saves you time. So the way I look at it is that anything you invest in something like that, if it saves you time, then it's what's your time worth, basically, is what it comes down to.
I've been telling myself that with the 3 nanometer filters, Jerry.
Oh yeah.
Because I figure it's time, and it still hurts. But one of these days.
Right. So what I'm doing right now is I'm turning on the mount and the webcam so you can see the telescope. So I'll zoom up on it too here. I got to set the exposure. Turn the gain down.
And our passengers, they can be doing all of this, all you see Jerry doing right now with this telescope.
Yep.
Go to our website, explorescientific.com, and we have the rentals, and you can rent this guy for usage. So everything you're seeing, you can do yourself.
So you can see the 165 up there. We've got a tall pier. It's a 7-foot pier, and we designed the observatory this way so that we could walk in with a full-size door and walk around it and change equipment out and do other things like that. But what I want to show you is how the telescope drive master works. So I'm going to get it tracking here. Oops. All right, I'm connected.
It's just full control over the system. You open the dome up, you focus.
Yep, everything.
And you can watch it all in real time. I think
I'm,
that's
yeah, I'm 5 miles away, and it's just like I'm sitting there at the observatory at the desktop working on it. It's real time, very quick response, no different, for me. All right, so I'm connected to the scope. Let me, I'm going to slew it. Let me start the chart program. I use Cart to Seal to navigate with, and you can see the area of the stars in there. Then you got this brown mess around the outside. That's our horizon. It's not very good, but it's good enough. It's like anything else, if it's easy and you got an opportunity to observe, then do it.
great. Sure.
That's the thing about
Sure.
what's the best scope to get, right? It's the one you use the most for whatever reason, whether it's light and easy to set up, or whether it's already permanently set up and you just turn it on and spend 5 minutes starting it up or something like that.
Mhm.
You know what I mean? So
Yeah,
that's what's
no,
cool about
I've
it.
heard that. I've heard that numerous times.
Yeah, and what I've discovered, with my sky surveys, for example, is, whatever piece of the sky you can see, there's a lot you can see.
There's
If you
always
just,
stuff to see.
there
That's
was
right.
tons of stuff to see, and I used to have an 18-inch, and now I have an 8-inch, and there's plenty of stuff that I've never seen because I just,
You had an 18-inch, Cameron?
yeah, I had an 18-inch obsession, very nice scope, beautiful
Wow.
scope, but you go really deep, and then but now to Jerry's point, even though you might have a limited sky, you can really see how that. I mean, there's that guy in Singapore who looks out his window,
Right, exactly.
in the apartment, and he looks for his 2 hours of guiding, and polar lined inside of his room there, and he just has a peephole, and he gets amazing pictures, and you can do some good stuff, whatever you have.
So if you look, I could actually open up the dome, but if you look there, you can see the telescope moving to this
Oh, yeah.
position.
Yep.
And I'm just moving it somewhere so that I can demonstrate the telescope drive master how well it tracked. And I've got a program I wrote that talks to it and shows you a graph similar to what PhD2 does, to show you, except instead of guiding, it's a tracking graph instead of a guide graph, because you're not, I mean, you are guiding it, but you're not guiding it through the sky. You're through an incremental encoder. So you can see the telescope there pretty well positioned to see the whole imaging train
Mhm.
and the scope. This dome is a 6-foot dome, and it just barely fits in there. That's why we don't have the dew cover on the or the dew shield on the scope.
Ah.
It's taken off, so because it won't fit. It barely fits. This is about the largest refractor you could fit within this dome. So I've got the telescope drive master turned on. I've got I've got a power switch here that turns on the cameras and the telescope drive master. I've got it turned on. So now let me bring up the program I wrote that shows how it works. It'll connect. It's an ASCOM compliant program.
Oh, you wrote pause. Yeah,
No, I didn't write POTH. I wrote.
Okay.
That always happens the first time. I didn't write POTH. I wrote this other program that I'm going to show.
Okay.
POTH was a part of the ASCOM platform. It was written by a contributor. Okay, there we go. Can you see that?
Mm-hmm. Sure.
That's the TDM drive
That's
correction.
the telescope drive master. Right. That's the correction it's doing. It does it 5 times per second. Now it's not going to, there's some little bit of lag in the display, but it should settle down here. Now I'm plotting a value, or I'm calculating a value that's a little different. So typically it's a little bit of statistical type measurement. And if people are familiar with statistics and 1 sigma and 2 sigma values, that type of stuff for error or for I'm actually calculating a 2 sigma value, not a 1 sigma value, which is typical. So if you talk about RMS, you say I tracked 0.8
Right.
pixels RMS or 0.8 arc seconds RMS, whatever it is. What I'm calculating here is twice that, and this right now is at 0.9 arc seconds, which would be equal to 0.45 arc seconds, basically.
Oh,
RMS.
wow. Okay. Okay.
Now it can do better depending on where it points in the sky. I've seen it get down to like 0.35 arc seconds is typically what I see, but we'll see how this thing, since it's settled out now, let me, I'm going to stop and restart it and we'll see what it's,
This is a G11 mount, right?
this is a G11, right?
Yeah.
And to tell you the truth, I've never adjusted this mount, and it was used as a, we used it in star parties, and it got shipped all over the United States, I think, before I got it. And, but it works.
You know what this is, if I might say, it shows you how excellent the G11 is in terms of PEC, because the TDM is just making it that much better, like you say, fractions of an arc second. But just the fact that there's no periodicity that you can see here shows you that there's not much periodic error in the mount itself.
Well, that's the thing. It corrects it in 5 times a second. It's much faster than auto guide would ever be.
Oh, yeah.
Oh, so you don't even see it. Yeah, that's a good point. You don't even see the error.
You don't, right.
Yeah, that's a good point.
So
if you let it, yeah.
So statistically, it should look like random noise, and which is what it is. It looks like random noise. That's what you see there.
Yes.
Now you do see a little bit of bias. You see where it dropped down a little bit and then came back. But again, the tracking error is a value, the average value plus or minus whatever the noise is. Okay, and that's what we're seeing there. And I'm kind of surprised that it's a little higher than normal, because typically it runs like 0.7 plus or minus 0.7 arc seconds on this scale. Oh, there it jumped down to 0.6, 0.7.
There it is.
So it depends on where it's pointing in the sky.
Well, and
really,
that is just, that telescope drive master, Jerry, that's just helping to remove one of those stellar imaging errors, correct?
That's right, exactly. So we can get into that a little bit. So did you pick out 2 or 3 ones that people were?
I did. Do you have a copy of your stellar imaging errors with you, Jerry?
Yeah, let me find it.
Awesome.
I'll
go ahead and tell the passengers. Jerry has made the taxonomy of stellar imaging errors that contribute to poor astrographs, and it's got it all, and it is. Let
me bring it up, and you want me to share it?
Sure, that would be fantastic.
Okay. So it'd take me a minute to bring up.
It's going to tell you pretty much every reason why you have poor astrograph photos, or astrophotographs. It's going to tell you the reasons, and you can go through and see why your pictures are poor astrophotographs as well. But it is technical, and Jerry can run the Large Hadron Collider and do just about it. But it's quite difficult sometimes to understand all that science and to understand the smartest guy in the room. And as we know, if you're the smartest guy in the room, you're in the wrong room. And so Jerry, just thanks for being here with us. I know it's hard for you to be in any room then, but I'm going to do my best for our passengers to try to translate.
Yeah, there's some really subtle things in this document, and then there's other things that are really, really more common that people will run into that they try to correct. And with auto guiding, for example. All right, so there it is.
I'll go ahead and tell the passengers too, if you would like a copy of either of these, if you just search the title here in Google, it'll pop up in our Groups iOS forum, and you'll see the link to download it as well. If you want the translated version, if you are an explorer and some of this is a little confusing and difficult for you to understand, then you can email me for a copy. Jerry title is a taxonomy of stellar imaging errors that contribute to poor astrophotographs. The copy of, or the title of the translation is "Why Your Pictures of the Stars Stink." It's a little colorful in the real document, but we know we've got viewers of all ages here.
I'm having some slowness with my machine is why it's taking me a while to bring this up. I think because I've got the
That's all right.
mount.
Oh, you're running a lot.
Yeah, I typically run a lot of stuff on my desktop, and this is just adding to it, I think. But I'm trying to bring this document over to my other display so that I can be looking at you and talking about it instead of looking off to the side like I am with the observatory. All right, I think I'm getting there.
But this, passengers, you want this list. You want it. It's fantastic, and it's going to tell you everything you need to know. So,
all right, here it is.
Got it, Jerry?
Yep. You see it?
Right. You know, can we just go to, if you don't mind, let me find it on here. Yours. Yeah. So, you have here the number one.
So number one, so shape error. Okay, you got oblong stars, right? So they're split up to two different causes. One is I call intrinsic, which means it's caused by your equipment. The other one is we get down to extrinsic, which is external to your equipment, right? Those are the two basic areas of problems. Let's focus on the intrinsic error. One of the intrinsic errors that you'll run into is, for example, sidereal rate error. Is that one of the ones? Which ones did you pick up?
That is a great one. That is a fantastic one. Yeah, well, I have trouble even pronouncing sidereal. I call it errors in space-time. Normally, if the battery on your hand controller is low, your stars are going to stink. Your hand controller, the clock might not be good, and so you're not tracking at the right rate.
Yeah, you could have some basic systematic error where you get your hand controller and it's not perfect, so you'll see a little bit of drift in your eyepiece as you're looking at the object, and you'll just have to recenter it. Now, there's other causes of the drift, so this is an important aspect of you can use these ideas here to troubleshoot your problem. But again, the problem is that you'll get the identical symptom that could be caused by 2 or 3 different things. Okay, and that's what this is. So if you're just getting a shape error, for example, it could be your sidereal rate's wrong, or it could be you have declination drift, which Cameron's going to talk about here in a little bit. There could be that's the polar alignment error. That's the other big one that people run into.
Yeah.
Right?
Yeah, that is for sure. We also have fun translations. You've got the mount orthogonality error, the MOE.
Orthogonality, right? That's right.
This isn't a perfect translation. I'll go ahead and tell our passengers, but it is my favorite. I call it the slewed too hard error. And this normally occurs very late at night after you've been slewing too many objects. You've been slewing one after another. You've probably slewed too many. And now your declination axis isn't 90 degrees from your RA, and your stars are probably going to stink.
Well, this could either be a manufacturing defect also, or it could be a damage, like you said. So if you damaged it somehow and your axes aren't 90 degrees, near perfectly 90 degrees apart, then you're going to have this kind of error, and it's going to cause drift. Yeah,
and the polar alignment error, I think, is a big one. I think it's an error of an error. It's a polar bear error.
Yeah, that's really the first one that people encounter that people tell them when they get on the forums. Well, you need to do a perfect polar alignment. Now there's there's a whole discussion about polar alignment that Cameron may get into about whether you need perfect or not. And I'm in the camp that you should never have a perfect polar alignment. I'm in that camp. And there's specific reasons for that.
Worms, Jerry.
That's a huge can of worms. That's right. And I don't know if we don't have time to talk about it.
That's gotta be, well, I need to know about it, but maybe on another show. I also liked 1.1.5.
1.1.5. Differential
Yeah.
flexure. Yeah, that's another one.
Yeah, differential flexure. A lot. You didn't tighten your screws enough on your guide scope. Maybe it's moving around when your mount moves, and so it's, you know, your guide scope and your telescope are not working together.
That's right.
So, but this is a great list. It will definitely, you'll definitely be able to figure out where the error lies.
Well, it'll give you things to look
8 of
for.
them.
It'll give you a lot of stuff to
Yeah.
look for.
Yeah, well, it is a lot. It is scintillating.
I
Just
think there's like 28 of these
20
things.
28, yes, sir.
So there's 28 different reasons why you have crappy pictures.
Yes, sir. Yes, sir. And
That are listed here. Now there's probably more. I expect there's probably more, but this is pretty comprehensive.
Well, if
list.
they run out of those, we'll make up more.
Yeah, we can make up more for sure.
yes, well,
That's right.
there are, yes, and you know, most of them are caused by us, and you know, nothing's perfect. No mount is going to be perfect, even though, you know, as a astrophotographer, a lot of the times that's what we want and that's what we're expecting. But these 28 errors that the great scientist Jerry Hubble has outlined for us, it is the best list that's out there. And it's awesome. So you guys really should look at it. It's just you know, it's a great educational experience, and you're gonna know what's going on. And yeah, so Jerry, thanks for sharing that with us too.
Yeah, thank you.
Yeah, well, it has been awesome. And yeah, I really think it's great because we've got the great scientists here, and then we've got the explorers. And you know, I think Jerry is that scientist who, he loves that adrenaline too. He is not in a lab coat. Look at him. He's outside.
That's right.
He's having fun. And you know, that's kind of what we're looking for and looking to create. Are the explorer scientists, because that's what we need. That's how we take care of our neighbors when we go and explore. You know, we're not leaving trash out. We're not creating more errors. You know, we're doing things right, and we are exploring scientifically. So that's a great thing. And you know, it's definitely possible. You can fly planes and crunch atoms too, and Jerry proves that. So thanks so much for being on the show, Jerry. It was
no problem. Thank you.
And now we've got drift alignment with Cameron. Cameron's going to go real deep and take us in with drift alignment.
All right. Hey, everyone. Okay, well, I'm honored to be here, kind of, you know, as a new person learning drift alignment by the gurus. I mean, Scott really helped me the other night, and by no means am I the expert, but this is a great opportunity to kind of, you know, show what I've learned in over the last week, and also Jerry, you know, as far as the mount is concerned, and all the errors that are associated with it. So please bear with me. I'm going to go through this, and then at any point put in your extra tidbits, because again, I am not the veteran yet at all, by no means, but I think I've learned enough to be dangerous.
Yeah.
So now we're gonna have some fun. So let's start off. Let's do this. First of all, I'm gonna share my screen. Scott gave me, and this is for everyone who's following along. Scott has published a cheat sheet, so to speak, on the website. And maybe Scott, you wanted to repeat that one as sort of the drift alignment, polar alignment method. And it's a nice couple of paragraphs which kind of outline what we're going to talk about today on how to drift line. And one of the things I learned the other day, and just to kind of set expectations, is we need to separate tracking error from pointing error. There's two different things. Okay, tracking error is your basically your polar alignment. Is when you're only tracking on one axis, right? And are you having drift, declination drift, as Jared was mentioning? So basically, tracking error is when the star moves away from where you want it, right? Or whatever object you're doing. When you're trying to take a picture or you're trying to look at something, if you're pointing at an object and you're trying to track it, that if any deviation from the center or wherever you have it, any change in the field is called tracking error. Now, the pointing error is when you slew between objects, and this is what Ross was referring to, when you slew a lot, what's going to happen is you're going to have pointing error because it's going to be relative to where you were last time, and there's an ephemeris. What's the right pronunciation, Jerry? What's the name of the mapping?
Ephemeris.
The ephemeris.
Ephemeris, yes.
Yeah,
The ephemeris celestial sphere, how that maps digitally into your PMCA with Explorer stars. What happens is if that gets shifted a little bit, then what's going to happen is you can have pointing error. When you want to go to a certain object, it won't be in the center of field of view. So there's two different things, but what we're going to focus on here, drift alignment, just to set expectations again. This is going to help you with your tracking error and basically your ability to follow an object, for photography, astrophotography, or visual. So like I said, I'll be kind of going through. So let me now switch over to, let me just go back here. I'm going to now change this to turn off my virtual background because I'm going to show you the scope and my setup here. So we can go through, that's good. Yeah, I think that's good. Okay, let me take this off. Okay, I'm going to make this full screen so that I can see what I'm doing. Whoops. What's going on here? How come I want to see that larger. How do I do that? Oh, I know what I'm going to do. Stop share. Yeah, I'm going to look at my video. There we go. Yeah, that's better. Okay, I want to be able to see this really large so that I can follow what's going on. Okay, so just to show you my setup. So here's my rig, okay? So I have a piggybacked Mach 102 on top of a C8 on an Exos 2 mount. And there's a beautiful PMC8 we were just talking about earlier. If you ever get one of these, it's a nice heavy piece of equipment, solidly built, mil spec. So, and then you see in the back, I have a right angle 90-degree 1¼ inch on my Mac, and that's perpendicular so that it doesn't change the balance. Okay, so as I rotate around, it's perpendicular, so that way when I'm looking through it, it doesn't change the balance as it's rotating around. And then behind it is a 294 ASI 294 digital camera, astrophotography camera, and it's tethered with the USB. I'll talk more about the details of that. And then to my right here, I have two tablets. One is with Explorer stars. We're going to use that for controlling the mount. And then we also have, if you can see here, this is ASI Air connected to the 294. Let me show you a little bit more about how I connected everything up, just so that we can see what's going on. Okay, so first of all, I already talked about the scope. Now, if we look at the PMC8 here, you'll notice that the right ascension, to avoid cord wrap, the right ascension is wrapped up because this doesn't move. The right ascension motor doesn't move. So you can actually wrap that up, and then it doesn't matter which direction this cable doesn't move. So that is the one cable. On the declination, this one, declination, you're going to want to have that as loose as you can, because that's going to be going all over the place. And the reason why this is significant is because of the, if you have cord wrap or anything, it can cause some drag, and that can cause some errors in your tracking and stuff. The other thing, what I did is, normally you mount the ASA, I have an uncooled camera, so that eliminates a power port. So I reduced cables by 1. Oops, this is not a good contrast. Let me go this, yeah, there. And I have just a single USB 3. And this again is a long cable. This is a 6-foot cable. And it's very loose because it's going to be moving all over the place as well. So I have 2 cables that are on the rotating arms there. Then, if we go down, I'm powering I'm powering everything with a 12 volt. I mean, let's go from the power plug here. So this is my outdoor cable. Okay. I have one 12 volt. This is a 5 amp 12 volt power supply. That's powering my ASI Air. The ASI Air has power ports on it, 2 amp power ports. The PMC8 only needs 2 amps, right, Jerry?
Actually, it's less. It runs. It can run. It draws about 500 to 600 milliamps at the most.
That's amazing. Even at 5 degrees a second slew rate,
Yeah.
that's amazing. So very safely, you can tether one of these guys. So that reduces your power. Now I just have a simple single plug, right? That powers both my ASI Air and my PMC8, right? All from the same. So that's tethered. You just have to enable that port, and away you go. Then the USB, the USB to my camera is of course connected to the ASI Air here. That's my 6-foot cable. And then I have an Ethernet because the ASI Air Pro doesn't have the new one. The ASI Air Plus has an external antenna that's coming out in November for those of you probably following it. But this is the ASR Pro. The Wi-Fi is terrible in this thing. So I actually plug in to the Ethernet, and then I use my own. This is a spare router that I happen to have, and this gives me great coverage. And then I can just set it up. So basically, I can go anywhere in my house with my tablet, and then the PMC8 has an external antenna as well on its own Wi-Fi network, PMC8, and that one's sufficient. Very good coverage with that as well. So I basically have 2 Wi-Fi networks, and I have a tablet. The tablets that I showed you earlier are connected to each of those Wi-Fi. One for the PMC8. This is Explorer Stars controlling the PMC8 Wi-Fi. And then I have my ASI Air going to this Wi-Fi. And then, like I say, I have 2 power cords. And what I do is I just flip this up. The blue lights, I just flip this upside down so that the blue light doesn't get in, cause any issues when I'm moving around. Okay, now let's talk about drift alignment. So what you do, right now it's pointing at the North Pole. You line up, let me just show you the controls we're going to use for this. You have azimuth and altitude controls for your polar, right? The first thing you're going to do is you're going to want to point roughly the tripod. So you're pointing this part of the scope, polar axis, towards the north celestial pole, which is the North Star. If you don't know what it is, if you can't see it, right, like Jerry showed some of the obstructed views, let's say you have trees blocking the North Star, you're going to want to use the compass and then look at the offset of that, and then basically line up roughly where the celestial North Pole is. Once you got that lined up, this is where drift alignment really plays off, because then you basically can use these controls, the azimuth controls and the altitude controls, to give the fine adjustments to get your polar line, even though you can't see the North Star. Now, the other thing you'll want to do is for the latitude you're at, you'll want to set the altitude adjustments. You're going to want to adjust these so that they are at your latitude roughly. Now, there's a little scale. I just go to the other side. On the other side, which you can see the numbers, you're going to basically, I'm in 47. So if you look at this, you can't quite see it very well, but anyhow, mine's at around 50 degrees on this, okay? So, but we want to just get it generally in the area, and then with drift alignment, when you adjust these, you're going to get it exactly to your latitude. So now, what are you going to do? So the first thing you're going to want to do is you need to point to a star at meridian, roughly at meridian, and the celestial equator. So if I share my screen again, let me just share my screen. And we're going to use Sky Safari just to give you an idea. And I'm gonna, let me turn this into equatorial mode. If you give me a couple of seconds here. I'm gonna go coordinates, equatorial, and then we're gonna wanna show grid and reference. You're gonna wanna show the celestial equator and the meridian line. Those are the ones you'll wanna show. Then, so you see how it makes a cross there. So I'm looking south now. You know, this is your meridian and this is your equator. You're going to want to point the scope. You're going to rotate the scope, loosening both your declination and your right ascension locks. Or in my case, I want to keep the park position line. So I'm going to keep the motors engaged, and I'm going to use Explore Stars to slew over to that location. And then what you do is, it doesn't matter which star, but you want something, I think you were saying, Scott, within 5 degrees of the celestial equator, right?
That's right.
Yeah, so within 5 degrees, it doesn't matter which star it is. So what we're gonna do, so let me go back to, I'm gonna stop sharing and we can look at the camera again. Okay, so I'm gonna slew, I'm gonna go 9, and I'm gonna go, let's go this way. Oops, sorry, 9. Yeah, there we go. So I'm going to rotate here. So that's
Moving
my
that manually. You doing it manually, Cameron?
yeah.
Or
I'm
you
just
can-
doing manual. Yeah, I'm
Okay.
basically I'm just pressing this
I
here.
see.
Yeah,
Mhm.
that's what I'm doing. Yeah. So I'm going to go, and then you roughly this is going to be parallel. You see that? Because you're looking at the celestial equator. Oh, sorry, this is for the meridian. Sorry.
Right, the
By
meridian, yeah.
adjusting the right, you want to get this will get you along the meridian line. And then what you want to do is you want to plan ahead a little bit. So depending on which side you want to do your tracking, whether it's west side, west the part of the meridian, or east part, keep in mind that when you're tracking the stars and you're doing this alignment, that you don't want to do a meridian flip, if you can help it. So you'll have to factor that in. But for now, I'm going to be pointing in the east of the meridian. So let me do that. I'm going to switch to declination. So now declination is going to be 90 degrees.
No, 0 degrees.
Zero. Sorry, it's at 90 and it's going to 0. Sorry, thank you. Yes. The north celestial pole is at 90. So now I'm going to point to 0. So here we go. Rotate that guy.
So your accuracy on the meridian, you want to be within plus or minus 30 arc minutes, okay? And you want to be within plus or minus 5 degrees in declination.
Yeah, so you can see, you can see here, this is at 0, right? Roughly, within 5 degrees. I'm just going to do this for purposes of the demo. I'll just kind of show you. You're going to look something like that.
Hey, Cameron, can I interrupt you real quick? I'm sorry, Cameron.
Go for it.
The source code creator is always busy and always has a lot of stuff to do. He's vice president of like 10 different things.
Yeah, you're the controller.
Go check
so
out
you tell
his
me.
stellar imaging errors. He's got to run. He's probably got to go jump in the plane and fly somewhere. But thank you so much, Jerry. It was such a pleasure.
No problem. I appreciate it. Thanks, Cameron. I enjoy. I'm looking forward to seeing the rest of your video a little later. So,
you bet. Thanks a lot, Jerry. You've been very helpful. Yeah. Take care.
Thanks.
Yeah. Thanks. So continuing along. So then what you're going to do is you're going to use your ASI airs, and I'm going to turn on. You're going to go. You're going to basically go into focus mode. Okay. This is one way. The other way is you have to have illuminated reticle eyepiece. If you want to do it visually, you're going to want to have one with red crosshairs that are illuminated, and you want to make sure that the eyepiece is orientated so that it's lined up north, south, east, west, right? So basically along the polar axis or along the celestial coordinates. That's important because then you need to know if it's drifting up. The star is drifting up, down, or left, right. So basically, we're going to go focus, and I'm going to go live. And this is just for the purposes of the demo. Right now, there's no star, but the advantage of the ASI Air, there's a little green box here. I'm actually, just to make it a little easier to see, I realize I have my tube assembly open. I'm gonna close it because it's too bright. So I'm gonna see better contrast here. Okay, there we go. Okay, there we go. So now you have a better contrast. Okay, so what you'll see is you'll see both the, there we go. You'll see this, you have this extra green box, which is kind of cool.
Yeah, I can see that.
You can move that around. Yeah, and you can move that around, and you can basically, you put a star near the center, but the most important is the star has to be kind of either above or below this horizontal line, okay? And that way you can measure what they call declination drift. So basically, because you need to have some measuring stick to be able to say whether the star goes up or down. And basically, you can use this green box as an extra measurement to kind of box in your star into that little quadrant to see if it goes up and down. Once you have the star, you basically just watch it. You start a stopwatch. You focus on a star. It could be any star. So you don't have to be fussy about, like I say, pointing error right now. This is just tracking. And then once you just watch to see which direction it goes. And then if it goes up or down, it doesn't matter. Once it leaves that deviates, you time about how long it is. And I think, Scott, you were saying, depending on how long of exposure you want, right? You basically, for your imaging or visual, you basically look for any drift within that time period. So what you do is you watch which direction, and then what you do is you adjust just the azimuth only slightly. So you loosen.
Know which way to adjust
you
it.
Loosen. Aha! This is a good question. Thanks, Ross. So what you do is you loosen it, and you just choose one. Make sure you know which one you did, and turn it. Let's say a half turn or something. And then you come back to answer your question, then you see which direction it goes. If it gets better, then hey, you're in the right direction.
All right.
And if it gets worse, then you have to back off.
Right. When you turn one of these knobs,
Scott,
you're going to lose your star that you've been tracking on. So, or it's going to move across the field. So you have to go and recenter the star back into the box, okay, so you can watch it if it drifts again, okay?
Thank you, Scott. And actually, I just want to add to that the beauty of this method is you don't have to be super fussy about which star. So if it moved a lot out of the field, don't worry about finding that exact same star. Find another star, and then recenter on that. And you can use the, this is where you can use your Explorer stars, Explorer stars to do some fine tuning and find yourself another star within that area. So you don't have to find the exact same star. That's not the important thing. What matters is that you're within 5 degrees of the equator.
All right.
Then
so you just make some.
What you do is
Sorry, Cameron.
Yeah. No, you're right on, and then you just keep track of which way you turn this and by how much, and sometimes you can overshoot, right? You might go a little too far,
Right.
And again, don't worry if the star falls out of the field of view. But what's going to happen is it's going to get less and less, and finally you're going to be basically zooming on probably to the same star, and then you'll see it move a little bit off the screen when you do this small adjustment. And what you'll notice is when you do this finer adjustments, the star will just move up or down, which is interesting. And you'll start to recognize as you turn it, which direction it's going. And basically you just keep on recentering. Finally, when you're satisfied that, hey, it's good, then we'll get to the next stage. But before I do it, I just want to set expectations as well. What I also learned from Scott is that what you will notice though, is what they call periodic error, which means the star will move from the left to the right, okay, and right to left. They'll have a periodicity where we'll start to kind of make a sine wave, you can say. It will move to the left and then it will veer to the right. And that will take a period of, I think, around 10 minutes or something like that, right? It might move initially a little bit fast, and then it will start to get into this rhythm after a period of, let's say, 10 minutes, where it goes back and forth. But you don't have to worry about it, because that's the same with any drive. Every drive, unless you have what they call permanent periodic error correction, it's a lot of expensive stuff that you can add to your mount, or a TDM, a telescope drive master, you are going to have periodic error, and it's going to move left to right. But you don't have to worry about that for now. And also, the way you compensate, either with a telescope drive master or with a guide scope with PhD. PhD, push your dummy, right? That's going to compensate for your periodic error left to right. But the advantage is that once you get this drift alignment good, you're only going to have to do that periodic error adjustment on the right ascension. You're not going to have to do it on your declination. So that makes it a lot easier and much more accurate.
Well, I've
So
seen that
you only have to
box,
compensate
Cameron.
for left, right.
I've seen that box
Yeah.
on PhD where it's like, only do the RA, and I didn't really understand why you would only have that box checked, but now I know. So,
Yes, and you know what?
do you think it's going to take to do a periodic, or to do this drift alignment?
Well, you see what we've done. We've taken, let's say, 10 minutes so far.
Okay.
I would say, Scott is suggesting, I've only done it one time now, just to be fair. And it took us about an hour, and we got it really darn good, really darn. I was kind of lucky too, because I already had it pretty lined up, and it was very satisfying. So we had awesome tracking. But I would set expectations give yourself between 1 to 2 hours initially. And I think when you get good at this, and especially if you put down markers where your tripod's going to be, or you have a semi-permanent setup, then you basically are going to be getting really, really good at it, and you'll be able to perfect it and tweak it and tune it, and you can, then you can just keep on calibrating, and depending on how accurate you want. If for visual, you can do it pretty quickly, right, Scott? I mean, I think you can do this pretty quickly visually, but for if you want to do 5-minute exposures and stuff like that, then you'll want to take longer.
If your
but anyhow, so that's
your exposure times are 2 minutes or 5 minutes or whatever they are. Leave the your testing time to be. I like to use double the exposure time that you want to. So if your maximum exposure sub is say 3 minutes, then go 6 minutes and see if you see any drift. If you don't, then that's going to be good enough.
That's perfect. Yeah.
If you were shooting film, you want to junk all your CMOS digital cameras and go straight to film in the future. I doubt if anybody will do that. But our exposure times back then were 30 minutes, 90 minutes, and so you would do drift alignments testing for an hour to, couple hours, maybe 3 hours. And so a lot of times back in the day, we would go to a site, and the first whole night, on maybe a 3 or 4 night sequence, first whole night was drift aligning. Okay.
Wow.
Now you don't have to go that crazy with it, unless we're building a permanent observatory and you just want this thing to be tweaked, okay?
Yeah.
And then you can do that.
The nice part about drift alignment.
I've always wanted to know how to do it.
Yeah, and it's very meditating. I mean, it's you just get some binoculars and hang out, and you can do this before, you can do this even in twilight, because it could be any star. And Scott was saying, you can already start, and that gives you your scope some cool down time. So it could be part of your routine, and it's a very relaxing way to really, you can get a good sense on how good your polar alignment is without having to you know, I'm getting older now, and I don't like to go on my knees and look underneath the polar polar finder, right? And this is really relaxing. And if you have an imager, as I was showing you, you can do this real time with with your imaging system with these crosshairs. It makes it very it's a really fun thing to do as part of your workflow. So that's what I'm going to be integrating into my workflow going forward. But it's not finished yet. It's not finished yet. This is that I just did the azimuth control. Okay, so that's the azimuth.
Yes.
Now we go to stage 2, and it's the same thing, but the difference is now I'm going to rotate. Let's go to the east. So is that no, the other way? So I'm going to go to the east a little bit, and you're going to rotate this. Again, I'm just using the slew controls, but and I recommend, it's good to do it that way, because then you can keep your park calibration. But you can, if you wanted to do this, you could release the clutch and then just quickly get to where you want. If you want to just do visual, and then that would be perfectly fine. So you can just release it. So what you do is you keep it going until you see the angle it's at right now. It's roughly, I'd say, 30 degrees. You probably want to be, I think, between 25 and 35, right, Scott, off the horizon?
Yeah, 20 to 30 degrees. Yeah.
20 to 3. Okay, 20 to 30. So right now it's about 30. So let's go. It just depends. In my case, I have a hedge that kind of blocks my view, so I can only go around 30 degrees. So I think we were around 32 degrees. But let's go a little bit more for those of you who have the advantage. So let's go. And keep in mind, when I did that, I only rotated on the right ascension. I didn't play with the declination, because we're still within. Yeah, you only change the right ascension. So basically, because your declination, you still want to be pointed at the celestial equator or within 5 degrees of that. So then you basically you can see it's roughly, if I just kind of hold this parallel, it's around 25 degrees, let's say, off the altitude. Then you do the same thing, and you basically but the difference is, and you still look for up and down movement, by the way. You still look for above and below the horizontal line movement. Same thing, but the difference this time, which is really cool, you basically, you leave those guys alone, don't touch azimuth, but you do these guys. You do those guys, the ones with the little turnbuckles, for your altitude, for your altitude. And the same thing, but they're a little more tougher because there's weight on them, because it's not you don't have the equal tension on both. When you loosen one, you're going to notice it sinks and stuff. So you're going to want to, I think Scott made a good suggestion, just put some a little bit of grease, right, on it to make it go really smoothly, right?
Yeah, your adjustment screws, you can just back them out entirely, put some like white lithium on them, screw them back in. And this just gives a real nice precision turn, So put it on the tip, on the altitude adjustment, okay, or latitude adjustment. Put it on the tip of those screws, because you literally have a screw that's just turning against a casting and so if it's got a little bit of grease on it, it's not going to kind of walk or make the mount move this way or that way or twist, It's just going to push and move it up, which is what you want.
Okay. Yes, and the key thing is, regardless, is you don't want to turn these guys very much, because they're quite a bit sensitive. Because
and you should be already pretty close.
Yeah, when you do you hope to get pretty close to start.
Yeah, exactly, and the advantage you have on the altitude part is, if you know your latitude, you can be within 5 degrees already, just by lining up those marks on the altitude, lining that up with your latitude, and then basically you're already in the ballpark, and then you just have to do a little bit of adjustments. Same thing, you come back to your reticle and you look at any star that you can fit in there, just line it up into that little box, and then watch it going up and down, and then watch which direction it goes. And if you have to do a big adjustment, then but I would still recommend, don't do big adjustments, just do little, mainly to figure out which direction the turns go. Then once you know which direction it goes, you can either, you have to do either more or less. You'll see the rate in which the star drifts north or south or up and down. So that's basically it. And then once you got that, and then you're still going to see the periodic error. The star is still going to move left and right. That's fine. That's normal stuff. But once you got it so that it's basically staying, like Scott said, maybe let's say you want 5-minute exposure, go twice after 10 minutes. It's once it's there. So you can see quickly that if you're lucky, you can do this technically in a half an hour, but I would budget, 1 to 2 hours initially, and then you're going to be doing 10-minute time stopwatches every time. But if you start to see it already drifting earlier, like in a minute, it's like really cruising off, you can cut that, and you don't have to wait anymore. You can just do your adjustments right away. And then you do that will cut down your time tremendously. And then if you get really good at this, then you can you'll get a feel for how much you have to turn to be able to change the rate on the altitude or azimuth. And then you're good to go. So, and then have fun, man. You're gonna be tracking, and you're gonna be cruising. So that's my
Yep.
that's my little update.
You can get started before it gets truly dark, so, if
Yes.
you are in the evening sky, maybe 30, 40 minutes or before it starts getting dark, you can start that drift alignment then, before you have to,
Yes.
And so that way you don't eat into prime time imaging time, so.
Well, I
I'm
think
just going to park my
you can,
scope.
get started early and get that precision that all our passengers are looking for. All our astrophotographers, they really want those tight stars. That is what makes a good photo. And the intro to the Stellar Imaging Errors by Jerry Hubble will certainly tell you that, and tell you what the scientists are looking for when they see your photos. And so, passengers, it's been a long show today, so I'm going to try to move fast. We are cruising, like Cameron said, and for most of us, for a lot of us here in the United States, it was the first real new moon of the year that didn't really seem to have rain. At least it was for me. So it's been a pleasure. I've been out a lot, and just sticking the telescope up there, pointing it at the sky. And so I want to share with you what's been going on this week while y'all have been sleeping. Captain Roberts and First Mate Gillis and myself, we've been working this whole time, and I got to collimate. I went on Saturday, and I got to collimate a big ED 152. And I talked to the guy. He's a legend from the Philadelphia area. His name is Mr. Bannister. And one thing about talking to a guy from Philly is it's just like that accent. It just, I don't know. It makes me feel cool, and it makes me want to hang out and just be his friend, so I can be friends with somebody who has that awesome voice. But what Mr. Bannister told me was that he and his mom, they love the show, and that his mom just keeps asking. They get to make moments together now. They are creating memories together, and so he bought this nice telescope to spend time with her. And so she's always calling him. She's asking him, when are we going to walk across El Cielo again? And so thank you, Mr. Bannister. I was really, really glad to get to collimate your scope. You are going to love your new monster, huge 152 ED, and your mom's going to love it too. But I think your mom enjoys something else more, probably the time she gets with you. And I also got to speak with another incredible person, probably a future APOD winning astrophotographer. She just got the brand new Moonlight focuser, and she's putting that on her 127 ED FCD 100 glass. And I'd gotten her that scope, and she is just blasting up that learning curve. And she's going to take better photos than most of us. And so she called me again this week, and she's got, her name is Miss Betty. And I really like Miss Betty. She has a deep connection with the Jovian planets. And truly, I tell you, Jupiter is in her blood. And so she has boarded the mothership now, and she had to bring a friend with her. She couldn't come alone. She really wanted a friend to come with her. And so Miss Betty, she called me and she said, I've got to get you, you've got to build me this scope. I need it now. You know, I don't care. I've got to have something. I said, okay. I can do that. You know, whatever you need, Miss Betty, I'll get it done for you. And she said, well, I'll buy this scope tomorrow if you can get a picture of Jupiter. She'd buy it for her friend. And so I had to go get her a picture of Jupiter for her. And I wasn't sure if I was going to be able to. It was a big challenge. And, you know, you really never know if your equipment is going to work. There's always something that goes wrong. And, but that wasn't it. It was, I had a prior commitment, and I had made a date with this sweet little lady that I've gotten to know here really well, being aboard the mothership. She's my friend. I definitely call her my friend, and the mothership, it could not fly without her. And so I was going to her house on Tuesday evening, and I would be showing her grandson how to travel through space. And she lived pretty far away and far from the city lights, past the Osage Hill to where it meets the Kituwa Pass. And I got there, and the three of us stood around the telescope while the 10-year-old star hunter listened to the orders, controlled the mount, aligned it. He did it all. And soon that little star hunter, he was seeing Jupiter for the first time in his life. Now that young hunter, he can navigate the summer triangle looking for game. And that star hunter, I think that night he got a new name. And I think I'm just going to have to call him Orion from now on. So I can't wait to see him again. Can't wait to spend some more time with those great people. So, but I finally got home. It was cloudy and I still had work to do. The sailmaker doesn't sleep much. And so just before 3 a.m., there was a break in the clouds, and I tried to get it focused fast enough, and the spacing wasn't correct. I could never get it correct. But the clouds were coming. I got it. I'll show you the photo. It's not very good. But it did sell scope. And so I will share a screen real quick. Like I said, we've had a new moon. I guess this one's for Jerry. It's the black and white Andromeda Galaxy for Jerry. But this is Betty's Jovian planet. I was wondering if I should even share it today because this photo's hers.
Wow, that's great.
Yeah, it's a single 0.2 seconds. I should have done shorter exposure, but it was what I could do, and I was
That's one of the lucky images.
That is a true lucky image.
Nice. You can see the festoons and the. I love that.
Yeah. So it was fun, and I felt really lucky to be able to get to do that. So few things have happened while y'all were sleeping, and I couldn't tell you everything. I just give you a little astro photo of it. So, it's got a little bit of noise here, and if you want to calibrate it out to see a little deeper, you can, but because just over the Osage Hill, next to that Kituwa Pass, my sweet little friend, a crew member aboard this mothership, she is the ship's surgeon, and her smile, it can heal you. And even though she's just learning how to use a telescope, she has lived in the star house for a long time. So passengers, you're almost asleep now. I know you're tired, and the week will go by fast. You can relax. I hadn't mentioned it yet, but the farther we go, the farther we get from home, our passengers, we need to feel secure. So I'll go ahead and tell you, we are prepared for any attackers, any intruders, any ne'er-do-wellers. It is true. We've got all these Alpine spotting scopes. They're looking out everywhere. One customer told me from San Francisco, he could see the rust on Alcatraz. And we've got these awesome binoculars from Alpine. We've got night vision. We've got game cams so we can see if anybody's walking around the ship where they're not supposed to do. We've got range finders. We have got you protected. You have nothing to worry about while you sleep. Because we've got Alpine on our side. So you can go to Alpine, Google that. We got a lifetime warranty. It is incredible stuff, and I'm really happy. So we're looking out for you. and we're not going to sleep until we get there safely. So trust Captain Roberts. He's been there before, and he's going to take us where we got to go. So that when that next supernova explodes, we'll all be capturing it, just like that Mark Slade Observatory. We will all be capturing that supernova. And so I'll leave you with a line from the MSRO website, a phrase written on the walls of the mothership itself, a certainty, and it's a guarantee to all of our passengers. And it's the reason you can sleep soundly, because all who board the mothership will be just like Mark Slade himself, forever remembered through the stars. We'll see you guys next week. We've got another good episode coming up. Thank you all for letting us be here. Thank you, Captain Roberts, for everything you do.
Okay. All right. That's great. So I wish everybody that was watching today that they got some good information. There were some questions. Jeff Weiss says, do you use the slew controls to recenter the star? And that's the target star that you're watching to see drift. Yeah, it's probably best to use slew controls because you're looking typically at a pretty high magnification, and the higher magnification you observe the star with your crosshair, the faster you'll see any kind of drift. So if you're doing it visually and you got a crosshair eyepiece, a lot of those crosshair eyepieces are like in the 9mm focal length range. When I would do it visually, I would use like a 2x or 3x Barlow and really crank the magnification up very high so I could see, or I could detect movement going north or south right away. If you're doing it digitally through a camera, magnification is still going to be pretty high. So, so it's something you definitely want to use. The electronic slow motion controls to recenter stars. You can always try to recenter the star you were working with, but if you're making a pretty big movement to make the correction in altitude or azimuth, you're going to see the star that you're working on probably fly out of the field of view. And so just work with another one that's plus or minus 30 arc minutes on the meridian. When you start the first phase, you want to be plus or minus 5 degrees in declination of being at 0 degrees declination on the celestial equator. For the second part of it, when you're working above the horizon, don't go too much lower than 20 degrees, because then you start running into effects from atmospheric refraction. And atmospheric refraction will do some strange things. It will move stars continuously depending on how high you're aiming. And so as you're tracking atmospheric refraction, as you go up higher in the sky, it gets less and less. Okay, so this is why another reason why you'd want to start looking the east horizon, because you want your telescope to be tracking higher to eliminate that atmospheric refraction problem. So
yeah, that would be like,
that answers it. You're gonna, but dive into it, guys. Try it. Give yourself an hour or two. You can follow along with the written instructions that we have, but you can rewatch Cameron's demonstration and get a good feel for it. And if you run into real problems, you get stumped, give us a call. We'll work you through it. And once you've done it 2 or 3 times, you're going to have it. You're going to know what to do, and you'll be making the most precision polar alignments of your life. So.
Yeah, and just to expand, I think if you don't have a motor drive, if you have like a first flight equatorial or any manual, you can use the manual slow motion controls.
Yes.
And then the reticle, and then basically just keep on rotating the declination. The right ascension to follow the stars, left to right, east to west, and then just look for the drift up and down. So because again, it doesn't matter the left, the east to west motion; it's the up and down that you're compensating for.
That's
Yeah.
right. I
So-
have had people ask me, can I use my 8x50 viewfinder with the crosshair to do this? And the answer is no, okay? Because you got such a wide field,
Yeah.
low power, that's not what you want. You want narrow
no.
field, high power to do this. So as much as you can get. Next week, we will have Dr. Daniel Barth for another episode of How Do You Know? We've got the 62nd Global Star Party, a celebration of John Dobson, John Lowry Dobson, and his incredible contribution and effect on the worldwide community of amateur astronomy. So it'll be really cool. A lot of people that knew John Dobson will be on the program, and so you're not going to want to miss it. And I think that's it.
Okay.
Let's just send people off. I hope you got clear skies, that you guys keep looking up. Hope you see an incredible bolide streak across the sky. You come home with some great images of some sort, and get ready to share those with us. So we'll see you next
Send them
week.
to me. Send them to us. Yeah.
All right. Take care.
Bye, everyone.
Captain.